Now let's take a look at this example that we just did, but now we're going to take a look at it graphically to see why it makes sense. We started with this idea of the integral from 1 to infinity of 1 over x squared dx. And if we look, this is a graph of 1 over x squared. What we're finding is this area under the curve. We found that that area converged to 1. What we're really interested in is not the function 1 over x squared, but the infinite series from 1 to infinity of 1 over n squared. And as we know, that looks like 1 plus 1/4 plus 1/9 plus 1/16, and so on. I still have here a graph of f of x of 1 over x squared. But my goal now is to find these numbers in my series within this function. So really what we're looking at is a right-hand Riemann sum. If we plug in 2, we have a rectangle height of 1/4. And again, we're still looking at this area under the graph of 1 over x. But 1/4 fits within that area. Next, if we go over to 3, we have a rectangle of size 1/9. That's still underneath the area that we found in the integral. Next, we can look at 4, and we know that that has a height of 1/16. Again, that is still underneath the area that I looked at with the integral. This means if the area of the integral over here, if that converged, then 1/4 plus 1/9 plus 1/16, so on, is always less than that area. Therefore, it's always going to converge as well. I do want to make note that we have a 1 out front here, but if all the rest of this converges, adding a 1 isn't going to make it diverge. It's still going to converge. It is important to note that this sum converges, but not to the same value as the integral. We can't find, using the integral test, exactly what the series converges to, because it's always less than the actual integral value. But we can say that it definitely converges because it lies underneath that continuous area.